Yeah, so tactic proofs are always backward reasoning, but there are tactics like ASOP and grind and so on internally do forward reasoning as well as backward reasoning. Yeah, so couple of other things. So let me answer Sunil's question. Can you do it any other way instead of doing these? There are many tactics which will one-shot this, starting with sim, grind, of course. And also another tactic which I can add to my list, it's called decide. Decide is where there is a decision procedure. This is a type class based thing, and I will not talk about type classes now. Maybe by the end of these 5 days, we'll have a session where we'll talk about type classes, maybe tomorrow or something. Right now, I just want to explain what tactics are. So there are many other tactics that would do it in one step. And now coming to the other thing, see, tactics don't always help. What happens is tactics change the goal. What if I did apply nat dot LE step here? You see something curious that has happened. What is the goal after this? I have to prove 1 is less than or equal to 0, which is false. So backward reasoning has this problem. We said this backward reasoning says that my final goal is true if this is true. And my final goal is true if this is true. But if I use it incorrectly, I could end up with, even if the original theorem is true, an impossible state. In this particular case, you could try. I'm going to copy this and show. So let me undo this. So this is an impossible case.
So you have to read it from the last if 1 less than.
No, so the way you do it in practice is you keep applying one tactic one at a time. See what the new goal is, okay, and do it. So now I'm going to show some baby automation here, absolutely baby automation, okay. So ASOP, which Ilya was mentioning, is far more sophisticated version of this. Baby automation going right and going wrong. So there is something called repeat. So repeat applies a tactic as long as it's valid. But now we have a problem because it was a valid tactic even when we had to prove 1 is less than or equal to 1. Okay. So repeat looked like lovely automation, except it was not. So that's why you have these search tactics which apply these things more smartly. So you don't just do these things. Okay. What happened is it repeated as long as the tactic apply was legal. But the tactic apply nat.le step is legal even if you're doing 1 is less than or equal to 1. So it applied it there. 1 is less than or equal to 0, which is false. What do we want to do really? What we want to do is at each stage, we want to try to show reflexivity. If reflexivity doesn't work, we will apply step. And I can do that actually in Lean by having first of apply nat.le refl, was it called? Refl, I used the other form. Okay, this time this is a happy error, no goals to be solved. Okay, so this is a little bit more complicated, but I just want going with apply tactic a little more. So what did this do? It repeatedly did one of the things. It tried these in order. So at the first stage, it tried LE refl, doesn't work. Let's try the next, works. Come back. It tried LE refl, doesn't work. This works. Come back. Keep repeating. At the third stage, LE refl work, done. Easy exercise. What happens if you flip these two? Yes, you'll run into the same issue we did before. The first one works eagerly to get to an unprovable state. Okay. So there's another this. First keyword means first of many tactics. It's like a try catch in many languages. Lean also has a try catch, but with tactic mode, it is the first applicable one of a set of things. Try this, try this, try this, try this. Error if all fail. Try this, except try this, except try this. So now it's working because what it did is it repeated 3 times. Okay. And let's see what happens. Exactly. It first checks if equality has come. Theorem 1LE4. I'm curious, so I'm going to print it. Okay, this was exactly what we were doing. It applies NAT LE step 3 times and NAT not LE. So my point here was exactly that we want to, what is a tactic? What is the automation? What is the proof here? Before you know what these things are. And I want to sort of say, we have seen simp and grind and so on. Rewrite, I'm not explaining right now. We have also, we'll see induction in the course of these proofs. So example, thanks. So I meant to answer because one of them asked. So example and so theorem and definition, I said at length, what is the definition? So example could be either a theorem or a definition. The difference between a theorem / definition and example is only that example doesn't have a name. If you're never going to refer to something again, you're doing it for purposes of illustration or maybe a test. Then you can, if you're doing it for testing or illustration only, don't bother to give it a name. That's all. Either theorem, definition, both work. Either of them can be called examples. So I can have so they have been theorems because usually you have examples of theorems, but I can even have, for example, NAT to NAT. I'm not going to use tactic mode, fun n to n plus 1. So this is an example of a definition of a function from natural numbers to natural numbers. And I gave it to you as it's an add one function, but I'm just illustrating. So I don't want to give it a name. Yeah. But this, yeah. In the first? In this one, you're saying. Why will it not work? Okay, let's do it. And I'll show you what happens. There are a whole lot of tactic combinators. Well, why would you want a last, right? Just change the order. I mean, so this was your question, right? You see what happened here? It applied it 4 times, and the net result was you got 1 is less than or equal to 0, which is unprovable. That's because this one applied, so it never tried the reflexivity. Okay. There are more tactic combinators, and you can write your own, which I'll do in a moment just for fun. But there's no real reason to write last because that's just waste. You can always put it in order. Okay. So I can make my own tactic by making a macro. NAT LE colon tactic. It's not going to be this. I have to say it's a tactic. No, I want this whole thing. Oh, sorry. What went wrong here? It should be in quotes. Okay. I have made my own tactic. It is called NAT LE.
There's no repeat.
Oh, I forgot to repeat. Thanks, Ajay. We just wrote a tactic here. Okay, of course, more powerful tactics need more work to write. But
Pipes.
that pipe symbol is simply the separator. Yeah, because commas and so on are often part of tactics. It would become confusing if, so it's not actually pipe. So it's just a separator because it will not collide with the notation that you usually have. Yeah, so this is the thing. Yeah, so Natalie, no, this is a tactic. You see, I've got it in theorem. So this applies for any L and any thing like that. See, this is not a theorem because if what is the statement of the theorem? If I give 20 is less than or contains false, right? So the difference, thanks, but this is an important question. Difference between a theorem and a tactic is a theorem is always true, while a tactic is the best effort to produce a proof, which could also fail. It could fail, it could make partial progress. So tactic can do 3 things. It can work, it can fail, or it can make partial progress. Well, a theorem is just simply a true statement. So yes, that's why this was a tactic. Of course, you can make much more sophisticated tactics, as I said, but this was an example where we just used macros to make it. Partial progress means like this applies, right? After this tactic, it was neither proved nor disproved. It just changed the goal. Yeah, that's what I mean by partial progress. It changes the goal. Yeah. Yeah, yeah. You can see the statements look slightly different. So maybe I'll go there and show you. So in short, any LE dot underscore reflexive is part of the definition of LE, which is itself an inductive type. And LE reflection is a theorem based on that. Where did I put that check statement? An LE step and LE underscore step. So this is a theorem which uses these, and it's deprecated. They're no longer recommending using it for whatever reason. While LE dot step is part of the definition of less than or equal to for natural numbers. Okay, so everything almost is defined from scratch in Lean, including natural numbers, including relations between natural numbers, including addition and so on. So this is what's called an inductive type. So one is more or less wrapping the other, but one of them is sort of at foundational, internal or foundational level, they're different. One is a theorem that uses the other as a proof, actually. Yeah. So short answer is a lot of compiler optimizations take place. When you export the code in Lean, it's exported in multiple forms. One is to the kernel, and kernel's duty is only to check correctness. And the other is code generator, and the code generator is meant to run code. Okay. Now you might ask, what if there are code generator bugs? What if it's proved correct by the kernel and the code generation? Unfortunately, there isn't a good answer to that. We would love to have verified code generators. We would love to have verified C compilers, verified hardware, etc., etc. And people are working on it. It's very far from achieved. Yeah. So these issues about mismatch between kernel. So kernel is not meant to be that efficient. It's meant to be sound. It's meant to be checked. It's meant to be at foundational level. But when you have multiple outputs, there is practical issue about matching, mismatching outputs and such things. And you would want to, so those are different levels of the chain which should be separately verified. You have Mario Carnero, who has a Lean for Lean. He has implemented Lean in Lean. And so certain other layers are verified because of that, like the type system of Lean. But many other layers, many people are working on verifying. But this remains an issue. So the separate pipelines solve one issue of performance at the cost of another issue that there is a potential soundness. Yeah. Huh? We don't really want to just trust it, but that's the best we can do today. That's all we can say. Yes. So there is how much your trusted code base is, and the work is always to reduce the trusted code base. And it's always important to keep trying to reduce the code base. But also equally important that you, at any given time, you know what is trusted and what is not. We don't want to lie about it. Okay. So yes. But that's why these questions like you ask are very important. One has to understand what is verified, what is not, and where you have an optimization, where is not, etc., etc. Yeah, so which order in which macros are resolved depends on priority, depends on which has come more recently, etc., etc. So there will be macros that are in Lean Score, there'll be macros in MATLAB, there'll be macros I add. All of them are iteratively resolved. Sometimes the rules are very complex, but in the case of macros, I think they're not so complex. Like class inference rules are complicated and brittle. Yeah, so. Okay, maybe, yeah, so any questions are welcome, but I'm here all week while Ilya is here only today. So if you have more questions for Ilya, I can also, of course, try to answer them.
They come on stage or
do
they come on stage?
Yeah, I think you can hear. Let's to prompt people to ask. Specifically, I think I should just say that you heard Ilya's talk, so you know what he works on, but he's also an actual computer scientist. Like, so if there are more PL questions, and especially compiler or whatever questions, take advantage of today having. Yes.
Great question. Okay, so it's actually interesting. So there is a very important notion when you do computer-assisted verification, which is called Trusted Code Base, TCB. So when people talk about TCP and they specifically talk about the size of TCB, that basically means the more code, the more likely there are bugs in this code, and the larger your TCP, the more likely your verifier actually has bugs that can compromise the correctness of proofs in it. When we talk specifically about SMT solvers, so SMT solvers are like very large piece. So if you looked into how even SAT solvers are implemented by like method of resolutions and like lots of, actually, I know that there's quite a lot of research done in, I think IIT Bombay on implemented SAT solvers. Anyway, so they are complicated beasts because precisely they solve and then the complete problem, and they need to be efficient on the practical instances. So when we deal with automated verifiers such as Daphne or Varus, I mentioned them yesterday, you trust the SMT solver. You trust this, I don't know, like 50,000 lines of C++ that Z3 is, or I don't know how many is CPC5. You trust that when it returns unsat, it actually done so correct. So, which is a big piece of trust, but the community sort of like accepted that as a part of the deal. And in case if you're wondering, like, are like 2 bucks and SMT solvers, are they common? Yes, they are. There is someone who has just graduated from ETH Zurich with the whole thesis and I think like 5 published papers at top level conferences on the subject of testing SMT solvers. Okay, there's a story about that. How the person responsible for maintaining Z3 at Microsoft, Nikolai Björner, got so annoyed at ETH researchers because they were basically just writing more and more fuzzers, submitting bugs into Z3. Many of them were duplicates, so he got sick and tired of fixing them and just like banned them from the tracker so they could not submit more bug reports. But by that time, they already have published a number of papers. And there was another story when someone from ETH did an internship, introduced a plugin to Z3 with a bug, and then left, and then another person from ETH found that bug in Z3 and wrote a published paper about it. So this is something that Nikolai Bjorn referred to as the ETH cycle of publishing, which is not entirely fair, but the point is SMT solvers are complex and they have bugs, so you can think it effectively as a tactic for discharging your goal. What happens with our trust? Where do we put it? Well, I mean, there are 2 options. So first, you can trust the SMT solver, and now in addition to the small and very, very well engineered and tested against 7 different implementation Lean kernel that Professor Schaper mentioned, you now trust the SMT solver. That's not great. So actually, in the demo yesterday, whenever I was calling the tactic that was using SMT, he had this blue squiggly saying that here you trust the SMT solver. So like beware of the boss. However, like people obviously thought about that. So when SMT solver gives you unsat, it actually goes through like a number of algorithmic decisions, but it also, what it might do, it might construct a trace of how it got that. This is actually something that has been actively studied. So Z3 doesn't do that, but CVC5 has a support for Lean. So what happens is when it returns unsat, it also does the proof reconstruction. So the reason why you might or might not want to have proof reconstruction is that it makes your proofs 5 times slower, because as an efficient procedure, it's written in C++, it does so fast, but then when the proof reconstruction happens, that actually takes a lot of time. But if you are interested in getting ultimate trust and removing the SMT solver from TCB entirely, that's an option for you. With the caveat that it doesn't actually support all the theories that CVC5 supports. So it's somewhat limited, but that's kind of the trade-off. So this idea of validating the solver results post factum is actually very powerful. And I was like, when we looked into that, so we didn't do that for CVC5. So that's the team at Stanford, like Clark Barrett. They did so that the tool is called LeanSMT, includes proof reconstruction. We actually use it in all our tools. I typically don't use it for demo because it makes things even slower. So we started to look into this idea of post-hoc validation of otherwise trusted proof automation. And it's very powerful. So for example, we have done it for other decision procedures. So the nice thing, so basically when you want to implement something, some piece of automation, you can write it as a tactic, and it's like very, like basically eliminates all the trust issues because the tactic, it produces proof terms and they are checked. But this is not how people outside of the interactive theory improving community operate. So typically they have some algorithmic idea of how to reduce certain verification issue to a decidable problem in automata theory, for example. I don't know, like to language improvement. And then they implement that in the language of choice, and that's effectively what the verifier does. So the nice thing is many of these decision procedures, and obviously one very interesting class of projects that people like to exercise is to certify decision procedures. So you basically have a theorem saying that when my decision procedure says that this statement is true, it's actually true. So it's sound, it is sound. Might be also complete, but people care much less about complete. Ultimately, you're using this thing, you not necessarily care whether they cover the whole space of provable things. Turns out that writing a certified decision procedure is actually like much more complicated than writing certifying decision procedure, the one that actually leaves some trace behind. So you can write a separate pass that renders this trace as a basically a bunch of hints into an input. And this is a very powerful idea. So we use it for like a bunch of solvers where you basically have the fast automation, but unverified when you just like doing the hacking or AI does the hacking. But once you have like this nearly 100% evidence that you got it right, modulo the trusted code base of your solver, you can also run this post hoc certification, which will produce the lean terms and will emulate the solver from the trusted code base of the transfer question.
The VS Code is wonderful that it allows you to verify imperative code. I wonder whether you have thought about the plans for closing the gap to real executable code, right? But just that I mentioned, hey, you like to verify C compiler.
No, it runs natively. It doesn't, I mean, it compiles to C. Ah, okay, yeah. Okay, so and you're concerned that we lost the guarantees because we trust the Lean compiler. What should we do? I mean, it's a complicated world we live in, so we might as well consider it as a world full of opportunities. So first of all, I'm surprised that no one yet got an ERC or something equivalent on the project called Lean Cert. Someone should really get onto that because there's a lot of, okay, Depeche is actually planning to work on it. So there's a lot of juice on verifying the Lean compiler itself, following the insights of CakeML and later ComCert. If you don't want to go into endeavor of verifying Lean compiler, which is also quite a moving target. So Henrik, whatever his last name from Lean, yeah, so he's like changing a lot of passes all the time. So other things that you can do, and this is where things get very interesting. So what you can do is do what people do in F-star with Pulse and Kremlin / Caramel / I don't know, I don't remember what's the current name, is emit the C that is, I mean, this is not what F-star does, but it's probably equivalent to your Lean. So the first step is instrument something like Velvet with separation logic, which we, by the way, already have done. The second step is implement something like a relational compilation in the style of for refinement calculus, or more modern stuff is what Clément Pitlaudel did for his PhD at MIT. And then effectively what you do is your compiler is the synthesizer. So instead of writing a translator and verifying it, you proof a bunch of refinement rule sounds, and then you make something like ESOP, do the search in the space of these rules. And if you manage to find a proof of refinement, that means that this Lean program or Velvet program is correctly refined by this C program. So your compiler effectively becomes a synthesizer. It's much more expensive, but well, nothing is impossible because we know automation and AI is good. So that gets you to the level of C, which is probably equivalent. So you don't need to trust the Lean to C compiler pass. So what to do from that point on? Well, sadly, this is like only as far the shell embedding will get you. At this point, you are at C, the level of C, so you might as well go and make sure that you are in the well-specified fragment of C, something like ComSort C. Well, I don't know, pay for Fable license and port VST. So because VST supports exactly this fragment of C, and from that point, you know that C is from it. Okay, so then there's also a compiler from C to ARM to x86, whatever. Well, again, we have ComSort, so we can do that. So yeah, I mean, basically there are lots of ideas lying around. What's the right way to connect them? I mean, I think that's very much an open question, but I think the Formula Methods community has tried all the different pieces. I hope it answers that. Yeah.
So the step when you're talking about Lean and C being equivalent, is this you prove it post facto equivalence or correct by construction?
More like correct by construction, yes.
So the compiler step itself.
So think of it as having a logic which allows you to take, I mean, okay, so basically like the logic that it's a relational logic that takes a Lean program and C program and gives you the rules that are like syntax driven to show the equivalence of the two programs.
Okay.
But then if you, I mean, this is a triplet, right? So but if you remove the C program from the equation, You turn it into synthesis problem. So here's the Lean program, here's the logic. Find the C program such that this statement is
You
complete.
use a solver to actually.
Oh, I'm gonna use ESOP for that. So this is actually
ESOP is also solver.
so ESOP is a solver. ESOP is a breadth first search in the space of tactical in the space of rule application. So this is actually a very rich idea. It's called deductive synthesis. It's by Mana and Waldinger from 70s, and the idea is that if you have a logic to prove facts about programs, you might as well use this logic as a vehicle for synthesizing this program out of facts. So you just exclude the program. And like they published a paper in 70s that tried it for like higher order logic and functional programs. Then it was sort of like resting there, and I think it was resurrected in like mid 2010s, mostly thanks to the work by Nadia Polikarpova, who used it with refinement types, and then Nadia and I collaborated. So we did it for separation logic. And as a result, we had the synthesizer for like a deductive synthesizer for C programs. But the starting point was not Lean program or not a functional program. It was a specification in separation logic, which is a special formalism to specify like C-like programs. So, but this idea of deductive synthesis is very powerful. So another instance of that you might have heard of is this framework called Fiat Crypto. That's by Adam Schlipala and his lab at MIT, who were at some point were attacking the problem of synthesizing provably correct cryptographic implementations from high-level descriptions of the algorithms. And the idea was actually to produce the code in C or on some assembly, I don't remember, from a high-level description. And again, that was done through this deductive synthesis refinement rules. That was pre-AI. Obviously, there was like a lot of manual work. I don't like Adam. He's like not big fan of using AI for this part of for this research. And he has a company that uses AI. So I don't know. So no one has tried to do fiat crypto with AI. I'm sure that will be a very rewarding experience on its own.
Isabel people in Metatasky and so on, I read their article.
Which one again?
People working on the Isabel system, they had this thing called Metatasky. A decade ago, I read their articles with the same idea that you write programs by saying what they should do, and
exactly
the solver should just generate it for you.
Yeah.
Not at this level, a more high-level mathematical kind of programs.
Yeah.
We're talking about this thing which Gen 3 modern AI.
I think they're in the case. Oh, yeah. So, yeah. Okay.
Is there some kind of translation validation work also in the?
It is very much in the spirit of translation validation. So what the translation validation does is, okay, if you like look at the works by George Nekola at certifying compiler, so it effectively produces the target program from the source program, and kind of very similar to the discussion about certifying SMT solvers that we just had. And it leaves the trace that you can render into the equivalence proof. So that's what translation validation is. So here, the same ideas. Okay, so here's one project that uses Velvet pretty much verbatim, unmodified. And you can see that this is from Facebook AI something lab. Those of you who know the luminaries of programming language field. So this is the guy who co-invented separation logic and correctness logic and many other things. So Peter Horn. So this is actually the work that takes a specification in the forms of pre and post condition, then uses like a ton of tokens because Facebook is rich, and produces a verified program. So yeah, like this is as complex as it gets. And I think they have had something like ICLR submission. Okay, so yeah, that's kind of flattering. You see that? When you have someone kind of vibe coded in the language that you have made, that's interesting. So, I mean, I have certain reservations about the framing of these contributions, because what they claim as contribution is we combine SMT solvers with interactively improved for LLM-based verification, produce the first benchmark tailored for our habit. I mean, technically, that means that they have used our tool. So, which combines SMT solvers with interactively improved. But okay, again, I'm not going to be too picky. It's nice that they're using it. So yeah, so this is one kind of this is one project that I'm quite happy to see that it happened. So I don't know if like many others that have a publication, but so Velvet was used in a couple of programming competitions based on Lean. So there was one by China Soft, which was in Beijing. We took an example from there. Another one, they're mostly local, sadly. I mean, like actually there was one international one. So another one was local Russian one, where I suggested one problem in Velvet, and then the organizers expanded it. And the last one was Verify This, which is the annual competition that happens at the ETAPS conference. It was in Italy this year. So there you can use whatever tools you want. So I sent a team of 2 of my students, and they use Velvet, and they got, like, I think the second place in the competition. So besides that, there's some interest. Again, the tool is very new because the official paper on it only got published like now. It's coming later this month. The tool itself has been around since like November last year. So another thing is, so this is the paper. It's kind of amazing because it's not even officially like fully accepted. It's conditionally accepted, but it already has 2 citations. So this is us doing a thing very similar to what this Vibe Coder does, except we go the full. So it's actually funny because Vibe Coder came out when we submitted this paper, so we were very surprised that someone else has done something like this. So this is us going the full length. So we start not from the pre and the post conditions written as logical formulas. We start from plain English text, and we go after lead code exercises. So and kind of okay, I'm kind of a little bit skeptical to the kind of research saying that we took an existing tool, we applied LLM for it, and it kind of worked. So I don't think it's that much fun. Mathematicians nowadays seem to like to publish these papers and like, oh yeah, here's my theorem, I used LLM and I proved it. And so even though the tool has been built by us, it feels like, okay, it's kind of not a very interesting result. So what turned out to be an interesting result when we tried to do that is that we were spending lots of tokens. So the question was, how can we produce? So the point is that if you have very powerful AI prover, everything is automated. You don't need to learn about tactics, so you don't need to learn about how to write proof kits. LLM don't need to bother using SMT solvers. LLM will do that for you. The problem is it's going to be very expensive. And if you're Facebook, sure, you don't really count tokens, but if you're a university lab with a limited funding, that very much becomes a concern. So what we try to do is to deliberately limit ourselves with the budget and see, if we only allocate $5 per medium complexity lead code task, how many will we be able to synthesize out of the selection of 50? So, and the answer is significantly more if we use Velvet. And the reason is that Velvet kind of gives you this really small and mostly tractable verification conditions that you can hit with SMT. Whereas if you try to do the same thing in vanilla Lean, then you will be forced to prove the general theorem, and for the model to one-shot it, it will require much more processing power, which I think is a very relatable argument. So investing into classical automation still very much pays off because it makes things cheaper. And this is kind of the point we make with this paper, because we measured it, we experimented with different proof modes, including testing specifications before you even try to do any SMT. And we found what we think is a reasonable combination that makes things very cheap. So you ask about other projects. Well, that's my project, but that's something that builds on top of Velvet. Anyways, so I think one of the first posts there is about Velvet. And then there is another. Actually, the first 2 posts on this blog, they very closely follow the content of the lectures that I've given. So if you want to have an alternative view, that will be it. But there are other stuff. So there are stuff on auto-formalizing type checkers in Lean. So I was very lucky to be invited a couple of months ago to Chennai by Casey. So I gave this talk there. I don't know if it's recorded, but I have a blog post about that too. So it's on recorded. Yeah. Okay. Yeah. So yeah.
With token efficiency. Yeah.
So we didn't compare with MVC Gen because at that time,
Or it may not have been stable.
yeah. No, the way we have kind of a love-hate relation with this MVC Gen, because Sebastian Graf started to work on it roughly at the time when we finished the first version of Loom, and so we mentioned that in the Popol paper, but then this story has a good end because Wova Gladstein got hired by Line Farol, and effectively him and Sebastian collaborated at unifying. And the problem with MVC Gen is was kind of limited in what kind of compositions of monads it was supporting, and Loom was designed to be much more extensible. So that part has been addressed, and effectively what MVC Gen is now in the newer version of Lean, that's what Loom is. We didn't compare it in this paper for synthesis because, frankly, I don't think that would add much value. So we didn't. Yeah.
Second is just my ignorance. What is separation logic? Is there can give a simple explanation?
Oh yeah.
Is it time to time? I don't know what.
for logic, as we know, I used to debug lecture yesterday, what should be a valid post condition? X is 1, Y is 1. I modify X.
It's so enjoys one again.
X is 2 and
Right.
Y is 1. Why this works? Because X and Y are two distinctly innate stack variables or just variables. So the model of the power logic is that we have arbitrary number of distinctly innate program variables. So when we change one, we know that we can change the other. Okay, now imagine that X and Y are not kind of scalar, like not regular variables. They are pointer variables. So I'm going to write instead of this, I'm going to write it C style, all right? I'm not going to draw the picture because that's going to spoil the surprise. So, and instead of this, because that's no longer accurate, because that variable like corresponds to some address, right? So, okay, instead to indicate the fact that this is actually some variable that stores some address that stores some value in the memory, I'm going to invent a new symbol, which is the same as maps to Italy. So, okay. So now I want to ask you, is this still valid? No. Okay, why not?
Let's say why may point to this.
Exactly. So we can have this and we can have X and Y both points into it. Okay, so how can we fix this?
You can take a precondition like not bind it.
Yeah, so there are two things. We can either strengthen the precondition, saying that X is different from Y, or we can say that, okay, if, okay, either, like, let's write like mathematical stuff as well. X is Y and X points to 2 and Y points to 2, or X is not the same and you get the idea, right? Okay, that was in the world where we only have two variables. Now we have Z points to 1. You see how this becomes problematic. So the number of your disjunctions is going to start multiplying exponentially. This is one of the main reasons why the Hoare style, the celebrated Hoare style verification that was discovered in late 60s, was pretty much dead by late 90s, because people realized that if you want to do it with for languages with indirection and realistic memory models, it will just not scale, that you will be forced to go that. The idea was very simple, and nowadays it's sort of folklore because everyone who has touched Rust knows about it, and that's like to do what Kenton suggested. Let's, instead of going this way and accounting for all possible LSN configurations, we will just add this to the precondition. This is not the same specification. This is a stronger precondition, thereby it's a weaker specification than what they had. But now we have nicely that X is 2 and Y is 1, right? So far, so good. Okay, now, I mean, this looks like it solves the problem, but it's highly non-uniform. Because, for example, what if we have the whole region in the memory that we described somehow, and we want to say that this, and at every pointer that is in this region memory, somehow is disjoint from any and other pointer in some other region of the memory that appears on our precondition. So we need to have sort of like better language to express them. And this is where the idea of separation logic comes in. So instead of using conjunction, which kind of is like very much in the domain of Hoover, so let's kind of lift these assertions and make them aware of the underlying memory model and impose this disjointness in the specification. So instead of using the conjunction, we are going to use this symbol called separating conjunction, star, or if you want to have like the roll of the tongue, within the sentence, people say and separating. X points to 1 and separately Y points to 1. So the nice thing about separating conjunction, and you see that over there. So this problem. So if you're familiar with Rust, that this is what safe Rust enforces on the reference arguments by design. So in safe Rust, the assumption is that all the arguments that we pass to the function as pointers, they are separate because in 99% of the cases, this is what we are. It's like highly unlikely that you will be passing LSS to the function. So this ostensibly simple idea just enabled so many things. So, and there's a very nice article on the history of separation logic by Peter Horn, that guy who is on the white folder paper. So let me show you like a couple of advantages that separation logic gives you. So if you are really stickler to the formalities, so you see, this is kind of non-standard logical connective, right? So so it only makes sense in the context of us running this program in fan heap. So now these assertions, they are sort of heap aware. If you want to define what the meaning of this logical statement, we say that this statement is actually something that describes a set of heaps. And by heap, I mean like memory model maps integer pointers to some values. So the idea is that something like x points to some variable a, that is modeled by the heap that is literally just x points to a as a single cell heap that has nothing. So a very useful assertion in separation logic is emp or empty heap, and that's modeled by a heap which is just an empty map. Again, please let me know if you're lost, but basically we are given a symbolic language to describe shapes of the heap in terms of certain bespoke logic, certain methodological formula. Okay, now what about this one? So this is actually very interesting. So when we say that this formula is true, where P1 and P2 are assertions following this language, so that says, so it's satisfied by heap such that exists H1, H2, such that H1 satisfies P1 and just regular and H2 satisfies P2, and who can suggest an additional constraint?
Is there
Q and Z. Yes. H1 is disjoint from H2. I don't know which symbol mathematicians prefer. I'm going to use this one for disjoints. I mean, I can say like something like we don't mention domain H1, domain H2. Here's the okay. So that's now you can see that we can scale it to many other things. So the real power of separation logic comes from the fact that now it can turn imperative style C programming into functional programming. So like everyone's favorite data structure is, which is kind of idiomatic to C, is linked list, right? So we have something like this, and eventually it points to zero. So this is something that when you write a C program with linked list and you ask to reverse it, so you start like drawing these strings on the paper and like starting to think about this stuff. If you think about linked list and you think about the list that we've seen on the tutorial on Lean, they're kind of the same things, right? Except the one is like nice mathematical object, which doesn't talk about like how it's positioned in memory, doesn't talk about the pointers. You only know that there's a head and there's a tail, and then the structure is recursive all the way down to the end phase. So now we have linked list in C, and we want to describe the memory layout that corresponds to this particular linked list, and we want to be able to prove programs such as reversing a linked list very much in the same way we prove programs of mathematical list reversal when you left. Turns out that this language is just enough for us, and we need to extend it with recursion, but I'm going to assume that these things can be recursive as definition. So if we extend this language with recursion, we can write a formula that can describe the memory corresponding exactly to the text. So, and this is actually very simple. So I'm going to say that list of the pointer x is defined as follows. So it's either x is 0, and the nice thing is that if you have an assertion that is not heap dependent, and the fact that whether x as a pointer is 0, it's not heap dependent, it doesn't look into the memory, you don't need to look into the memory, you can use ordinary conjunction. I mean, I can also use separating conjunction. So you see, this is one case. So case one. The second case is x is not 0, and x exists x prime b such that, okay, I'm going to have quantifiers there. That's legal. X points to x prime separately at x plus none. Yes, we have point derivatives. Points to b Separately, what's missing? We have seen the definitions of the mathematical list.
Disjoint.
Huh?
X prime is not in V or something disjoint.
Yes, exactly. It's not so, but we already have all the arsenal to say it. That's easy.
Oh, okay.
This is it.
Yes.
Now look at this. This is your nil case. This is your cons case. This is your tail. So you see, like, if this is x, this is sorry, yeah. If this is x, then this is swap that. Oh, so one is right. Yeah. So this is linear. This is x prime, and this is of x prime. So you see this idea of enforcing disjointness. So in functional programming values, they are like all separate, right? There is no such like atrocity as aliasing in functional programming. So by imposing this discipline of no aliasing between the pointers that participate in different assertions as addresses, we can limit this function. So basically anything that resembles a tree very naturally fits here, which is unsurprising because everything that resembles a tree, that's what functional programming has been made for, right? Graphs are slightly more complicated. There is at least half a dozen dissertations about how to capture the shape of decks and heap-based graphs. So if you have rich interest, here we go. So how to capture that using separation logic is all very interesting. There are some ways either extended or just unfolded in a different way. So actually, since we are talking about separation logic, I'm gonna give the most characteristic rule of separation logic that we don't have in the core logic, so to say. So notice this program. So it has stuff about x, stuff about x, stuff about x. And then it talks about y. So you see, if we also mention z, which will be separate from x and y, nothing really will change in the pre and the post condition. So this is actually a great property of reasonable programming languages, which most of them are except for JavaScript. The commands in these languages are memory local. So the fact that the command changes something in the memory leaves the rest of the memory very much unaffected. So this phenomenon actually is very well reflected in separation logic. So it's connective, and the memory that remains unaffected, it's called the frame, because it's kind of frames. So, and for that we have a wonderful rule. So imagine that you have managed to verify the program C with the precondition P and the post-condition Q in separation logic, right? So then the next thing turns out that if you manage to prove that a part of the heap is disjoint from the P in the precondition, or you just assume that you know by the properties of the language, and this is actually not a trivial fact, that's something that's in the soundness of the logic, the very same thing becomes unmodified. This is great because now we can have canonical specifications of programs that do not talk about the irrelevant stuff. So like this can effectively be gone from there, so we can verify the program against the minimal footprint, against the minimal memory that it actually requires to run and produces, and everything else can be just added there. Okay, so this is something that the humanity knew for 2004, 2002. There's a seminal paper by Reynolds, Peter Cohen, and Fong Sok Yang on the separation logic. So the fact that we can actually logically split the state between what is being modified and what's not being modified, that became immensely powerful. That's why we have Rust nowadays. So Rust is very much like exists thanks to separation logic because someone in Mozilla actually used this idea like that to show that we can enforce using the type checker. So a next push, I promise that's gonna be the last thing, but you probably to talk about separation logic. Should have allocated another 4 hours for that. Like in 2004, Peter O'Han wrote a paper whose title keep forgetting of something resources, locality, concurrency, introduced something called CSL, concurrent separation logic. And the main idea there that if we have a program which is the composition of two parallel threads, C1 in parallel C2, and we know that we can verify these things separately in isolation, then the beautiful thing is that if they actually require disjoint pieces of memory to run, then it will produce disjoint piece of memory. So if two programs work on disjoint memory, it's safe to run them concurrently. I think we can all agree with that. Okay, so this is like 30% of the aha moment of concurrent separation logic. The other 70% certainly will require maybe like another 15, 20 minutes. But like most of the programs that are concurrent, we don't always run on fully joint memories, right? They interact, otherwise they're kind of useless. And the way we interact is by locks. Well, mostly. I mean, you can also use like fancy primitives like compare and swap, but okay, 99.9% of concurrent programs that people write, their passing of information between threads happens through locks. So you take the lock, you do stuff, you release the lock. You have the mutual exclusion. But then it becomes kind of finicky because I've said, okay, this rule is beautiful, but only if programs never touch each other's state. But now we have the lock to which they actually can touch each other's state. But here comes the absolute genius idea. So what locks do logically is they make separation in space through separation in time. So let us think. So the fact that no one ever touches the same, I mean, for a well-engineered program, so no one actually ever touches the same memory by more than one thread at a time, because that's exactly what mutual exclusivity overlap gives you. This has been worked into the logic. So in this, there's this rule in which, like, when you apply the lock, you transfer certain piece of memory captured by separation of logic assertion from what the lock owns to the assertion of the program. And when you release the lock, you give it back. Locks kind of become slightly like a little bit like loops because you have what's called lock invariant, which you take when you acquire the lock, and which you give back when you release the lock. So people need the name, what to call this phenomenon of lock. It will be holding a piece of state that it gives and takes back when we acquire and release it. And they call that ownership, an ownership transfer. So effectively, you transfer ownership over a piece of mutually exclusive state from the lock and to the lock. And this idea that, in fact, you can orchestrate safe interactions between multiple parties, multiple threads. So this idea of separation and ownership transfer, that's what powered separation logic from that point on till now. It's still going strong to the extent that it has been extended to message passing programs. It has been extended to authentication, like all kinds, like so many things could have been encoded through passing the ownership. And again, this is exactly why Rust has the notion of ownership. To the extent that some people in the community call separation logic an ownership logic, because the idea of owning the piece of resource, piece of memory. And by the way, it's no longer concealed to just like regular memory model. It also can be what's called ghost memory, something that is not physically present in the program, but identifies you like with certain things. The field grew super large. So separation logic is steadily like one of the most present topics at programming language conference, just because there's still this simple idea of separation and disjoint as ownership transfer. It solves so many problems. Like people say that separation logic was not unknown until it was discovered. And this is actually partially true, because if you don't know any of that and you start like trying to build a verifier for something like C programs, or you try to do something like modular tools that are agnostic to your surroundings, you will end up inventing separation logic. It's actually not that difficult conception. Okay, I'll just stop here.
If you ignore this magic id.run do, it's just like the corresponding Python code. Yeah, so sorry, this is an answer to a question which might be of interest to others and directly relevant to things like Velvet. Question is, can you write imperative code where you take a variable, change its value, and have a while loop in Lean? You can, but we'll do a even more thing. This used for, let me use a while loop. So you can do this thing that called id.run do, which means you're returning ID of NAT, and identity of NAT is the same as NAT. So there are monad introductions and we'll discuss them in detail at some point. But my point was, the question is, so this is imperative code. And so if you transpile from Rust or Python or Go or something, or for efficiency, very often you want to write imperative code, and you just can do it in Lean as well by wrapping it in some correct way. This gets rewritten internally. Let me do a version with while. Let me call it the same thing. Prime So let mute accumulator, let mute I colon equals 0, and let's say while I is less than n, do shut up for a moment, Mr. Copilot. I colon equals I plus 1, and yeah. Yeah. So this is a while loop inside Lean. And there are a few differences. You have to explicitly say a variable is mutable, which you even have to do in Rust, for example, and in any stricter language. And so if I don't say it's mutable, it will take a different copy for everything and it will go wrong. So let ACK is 0 will just define a new variable, but you're saying it's mutable. And you can, this is a typical Python like program. Other than that, while I'm incrementing I as I plus 1 and adding to the accumulator, and then I'm returning. In fact, let me rename this as sum instead of accumulator, which is more, ACK is a more typical functional programming thing. So you let the sum be 0, and while I is less than n, you're adding to I and doing it. So the thing is that if you generate code from Python or Rust or something, this is how it look. Efficient code will look like this. What Velvet lets you do, and MVC Gen we talked about, is prove things about such programs. So here you'll have to put a loop invariant, pre and post conditions, and do horse style proving if you want to do it. You can't do functional proving like you're doing with other things, or you can in principle, but it can become quite painful. Yes. Yes.
Is the spoken words here?
Yeah, by indentation. By indentation. Yeah. Yeah. Lean has a scoped indentation. Lean has indented syntax. It also allows other things, but it's actually much more liberal than Python in the sense that lots of things which would be Lean tries to understand your code based on indentations. And so there are often 3-4 different ways, all legal, of writing the same thing. While Python is much more likely to just give you an error if the indentation doesn't follow exactly what it wants. So Lean has this very sophisticated parser elaborator, which can handle variations. Like, for example, I've written sum is sum plus I. I could also write sum is sum plus I like this, and it understood that as well. Because there's no other meaning. Python, something like this, it would protest. I could do this as well. And I could do this as well. I mean, it's quite liberal about how you indent things. So long as it doesn't misunderstand or doesn't see a real ambiguity, it just accepts things. But otherwise, yes, it's indented. Just because of the do. So if I put this here, that would cause a problem. See, here it got 10 now. So certain things are strict because of real confusion. Everything after the do ends when your indentation goes back to 0. Okay. So yeah. So certain things will be wrong, certain things will be right. My point is that sort of like Python's indentation, except that Python's indentation quickly complains you're wrong, while Lean much more often understands things. So you can just indent things for readability, and it will accept it if it's unambiguous still. Can you see the C code that Lean generates? Let's try. I haven't seen it for a very long time, but it's generated because I built something yesterday. Okay, so ls dot lake, I have to find it. Build /ir, I think is where it is. There you are. Okay, let's look at quicksort C code. I have no idea what it'll come out. So there was a time in when I was working on a SAT solver in Lean where I was actually looking at generated C code to see where things were not. Mm. Let me open this whole folder, and then we'll open quicksort. So Okay. So there seem to be inputs. So as you see, it depends heavily on lean runtime, lean objects, but lean free object, X2, lean declaration, there's some go to. The real value of this C code, though, which is how I used it more than understanding C code. The one thing I understood from the C code is that if you have a structure with a mixture of propositions, I thought I was slowing things down because of propositions. I said they disappear from the C code. I'll open one and explain these things. But the value of this is you can use your C tooling. So when you're running things, there are all sorts of profiling tools and so on, which C, C++, Java, all of these things have, right? So those same tools, profiling tools, where the call traces where which methods are spending long time, you have to then guess which lean method it is and so on. All that works. And one stage in my life, I did use those profilers to do these things. I mean, those of you who know more software engineering will know what the tools there are. But yeah, so you can look at generated C code, but I think the bigger use is that, oh, I didn't have the C++ extension. Let me install it and it'll look nicer, which shows you that the last time I did this, I was using a different laptop. Yeah, so I think the syntax is there anyway. What I didn't understand the question. What's the yes? Why do you want to have the lean interpreter at all? Is the question. There are many reasons. One obvious one we have seen is when you do eval, it doesn't go to C. It just runs the interpreter. Also, internally, while it's type checking, it runs its own interpreter. Okay. That is already one reason. A second reason, though, is that, for example, what I do all the time in my work is I have the front end code, which is a lean zone interpreter copied and modified. When you're metaprogramming, you're generating lean code and you want to check if it is correct lean code or not. You use the interpreter and run it. You may even want to run it and extract the values. There also I do it. So that's right. So you have a compiler and you have an interpreter, and they have a lot of code in common. So there's the interpreter and code generation reason, but for both metaprogramming, but also for tooling, for using in VS Code, all these things, the interpreter is extremely useful. I mean, yeah, it's not just for the program, it's not, but of course, Lean is not used just as a programming language. So yeah, for the interactive mode, it's heavily used. There's an app uses what? Interpreter. Compiler. I mean, most of the ideas in Lean are picked up from many places. From Rust, from LLVM, from Haskell, from, as I said, work of Thierry Coquin, Martin Leof, all the way to Church's work in the 30s. I mean, so it's an implementation of accumulated ideas over a century, you would say, almost. Yeah, so an excellently engineered and with very good choices implementation in my view, but it's not some recent ideas, as I said, like FBIP. I don't know if I mentioned it here. So one of the optimizations done in functional languages is commonly is tail call optimization, but there's a fancier one called functional but in place, which came out of Microsoft research in an experimental language called Coca. I think as recently as 2018 or something. And that's part of Lean. I don't know if it's yet part of, say, Haskell or OCaml. I don't know if it's there it may not be there in OCaml yet. So ideas ranging from TCO and so on, which are part of Haskell OCaml, to brand new ideas like FBIP, which are not even in other mainstream functional languages. So you can say it has ideas from 1930s to second decade of this century implemented. Yeah, so grind tactic. Okay. I do not know too much. I'll say a few things. So it's a whiteboard forward reasoning tactic. So most of these tactics we are seeing are mostly backward reasoning. So it starts with all the hypotheses you have and then starts trying to deduce things from the hypothesis. So, and it accumulates facts. It uses various heuristics about what to retain, what facts to accumulate. It also makes external calls to many solvers. Okay. So it has an SMT solver implemented in Lean, which is aware of Lean's type system. So the historically important point here is Z3 was created by Leo de Moura, who also created Lean. So you have the world's expert in making SMT solvers was made lean. So it's a very high quality SMT solver. They have linear programming. Huh?
SMT.
SMT means satisfiability modulo theories. So it's a SAT solver with many special purpose tools, roughly speaking, for many solving. So it also has linear programming, linear integer arithmetic, LIA, which is one of the things. I don't know if it was mentioned in the talk here. Another conference it was mentioned. It's another algorithm. So many algorithms that are used for decision procedures in many specific domains are also called by grind. They're implemented in lean or sometimes external tools which generate a certificate which is then checked in lean. That is also done. You can also add your own custom solver so long as it meets the contract of taking as input the current grind state and giving it output a proof that can be checked by lean. So it's an extensible framework which has many components. It does forward reasoning, it does searches, and it does calls to many external tools. Yeah. Beyond this is, I don't know. Yeah. It's not very well documented. So, yeah. But then if you really want in lean, it being lean, let me look at a case of grind. Yeah.
It's common tactics, right?
Yeah.
Can you tell something about
Other tactics.
So that
Yeah. So ASOP is a search tactic. Okay, so ASOP works in many cases. Let's see, let me try one case where grind is here and let's try to use ASOP instead. So let's try here. Here, I can try ASOP. And ASOP failed to prove goal, unfortunately. So not a great illustration. Where SimpWorks ASOP will ordinarily work. Let's try here also. Okay, so ASOP versus grind. Grind seems to be a winner in this competition so far. Let's try in the exercise. It failed to make any progress at all. Okay, so it's not doing very well, but it's actually very good. So it's just that grind has got so good that we stopped using ASOP very much. So there are a few other tactics. ASOP is an automation tactic. It's basically a tree search tactic with backtracking. So it tries things like induction, it tries simplification rules, but simp is monotonic. Simp, if it finds a simplification rule that works, it takes that and goes ahead with it. And it doesn't backtrack. But ASOP does breadth first or depth first search of trying to apply various ASOP rules as they are called. These are instances of apply, rewrite, you can put a custom tactic. So it's a breadth first search on top of induction, simplification, and so, which tries to construct a proof for you. It's a deterministic breadth first search. Largely deterministic, maybe concurrency breaks determinism, but there's LLM or anything involved. Yeah.
So this grind, simp, and ESOP all are of same family of same type.
So no, simp, as I said, is completely deterministic, and simp is does not backtrack.
Yeah.
So simp, you can say, is a different kind of tactic. ASOP is a tree search. Grind has some level of tree search. The inner level, there are different details. So ASOP, grind, hammer, canonical, these are all automation tactics which are supposed to do a lot of things and try to solve for you. Simp does a lot of one kind of thing. Simplification only. But yeah.
So you're saying that grind might be a better, the new one, so it will take care of all the other things.
There are cases where simp works where grind doesn't work. Those are relatively rare. There are more common cases where ASOP or hammer works where grind does not work. So it's not true that grind beats everything. But grind is, usually if you want to use automation, you'll try all of them in turn, like this first of so and so, or you'll use you can just try them out in succession or something like that. But yes, yeah. So now ASOP will work where simp works. ASOP failed where grind failed. So this one, I tried it in the grind case. This one ASOP should manage perfectly well.
And what's the mistake?
Indeed, it worked. And ASOP also has a question mark. It's a search tactic. In fact, it found it as a single simp in this case. Yeah. So
will kind of automatically figure out what can go with it, right?
Yeah, so the question mark tactics are really of two different kinds. Simp, question mark, and so on are where it tells you replace this tactic by so and so. Apply question mark and exact question mark, on the other hand, are search tactics, which also tell you replace, but they also search. A simp question mark is not really, yeah. So they're telling you replace by something more specific in all cases. Yes.
Then we really don't know what to.
Yeah. So
Okay, what does which tactics brand use?
how can you get which tactic grind has actually used? You can set some option of grind or trace. I don't know the exact formula, but grind has very detailed traces. And if it fails, set option trace dot grind true in. Okay. Thanks for the question. Not very helpful, but it just said closed grind dot one, closed grind dot two. But yeah, so dot, is there an all or something? Debug. Okay. So yes, you have, so you can trace it. It's a good question. So thanks for the question. So people have been asking, huh? So set option sets an option. And when I say in, it's only for this command because I don't want to mess up the rest of my file. So I just set trace.grind dot, and you can autocomplete. How did I find debug? I waited here. And if it doesn't do it, I can hit Control plus and it offers various things. So the debug is .ac did not give anything at all because it was not AC, whatever that is. You hover on it, it'll tell you. But if I say debug, yeah, thanks. This answers a lot of questions of what did grind do. So there are internal things called adding 10, new root, so and so. Okay. It worked hard. That is the short answer. You can see membership.mem is what are all the theorems it used, how it found things. Oh
We
god.
cut off all the backtracking and so finally
No, this is only information. This is only logging. It has not changed the behavior of grind tactic at all. So this tracing options only tell you how much information to give me in my info view. This does not change the backtracking or anything. Yeah, Anirudh, what was it? To ASOP. Yeah, ASOP is also configurable. You can put it in square brackets, just like you'll do. Now, maybe the syntax is a little different. You can kind of click and see. But ASOP, you can pass lemmas. I've done it. I've forgotten how. You can hover on ASOP, it'll probably tell you, or somewhere ASOP document. I've forgotten. Since grind came along, I mean, for a while I used to use ASOP as the strongest thing in LeanAid, but since grind came along, I've hardly ever had, and hammer also. There's lean hammer, which is so between hammer and grind, I've never almost had to use ASOP. Hammer is another kind of automation tactic. So hammers are something that Isabel pioneered. So a hammer tactic is something which, given a goal you want to prove, writes it in a form that can be passed to an external SMT solver, calls the SMT solver. If it's successful, uses the output of the SMT solver to reconstruct the proof. So this is what a hammer tactic is. This is the general description. I think as Ilya explained, SMT solvers proofs may not come with certificates. So you don't trust the SMT solver. You use the information of the SMT solver to reconstruct the proof one way or the other, either from certificate or just from what theorems were used or whatever else as a guide to your own automation. So this is the general description of a hammer tactic. Isabel has had a hammer for a very long time. This has to do with the fact that higher order logic hammers are a lot easier. Isabel has a simpler logical system, which means expressivity is less, but automation is better. So Isabel has had a hammer as a core part for a very long time. Hawk, as it's now called, acquired a hammer maybe about a decade ago. And Lean Hammer came maybe a year ago from Carnegie Mellon University. There was First lean hammer project was abandoned. Actually, Gabriel Ebner worked on it for his thesis, and then he moved on to other things. But 1 year ago, lean has its own hammer. So hammer tactic is one which again generates proofs. I mean, like your sim question mark grind, etc. It generates a longer proof and gives it to you. But again, they're not comparable because they're all broadly search tactics. But if you get to what solvers they use, so yeah, your point is correct that both use SMT solvers. But in both cases, SMT solver is only one component. Hammer also uses induction, it uses a whole bunch of things. So the difference is in the details. So fundamentally, they're both automation tactics. Fundamentally, they also both use external, there's as far as SMT is concerned, there's a fundamental difference. Grind has its own mini SMT solver inside Lean, fully implemented by Leo inside Lean, while Hammer calls an external SMT solver, Z3, CVC5, or whatever else, as does Lean SMT, and reconstructs using that. So at the SMT solver level, also they're different. But as I said, SMT solver is one component of both of them. The rest of what they do is quite different. Yeah. I don't think so. I think Hammer can still do things which Grind cannot do. But Grind runs fast, Hammer runs slowly. People were working on Grammar and Hammer, and people were working on Grind. Hammer came first. Grind came some months later. Then Grind got better and better and better. Given Grind exists today, perhaps nobody would start working on Hammer today. Okay. So I think the increment, Aesop is even older than Hammer, quite a bit older than Hammer. Janis Limburg wrote it. It was the first search tactic actually in Lean. So in some sense, if Grind existed, you would maybe just add more features to Grind or write a light wrapper around Grind rather than re-implement from scratch. So I would say that, yes, given the existence of Grind and its extensibility and so on, I don't think today somebody would set out to write Aesop or Hammer. That the additional features are too little to justify bothering to do it. There is something called canonical, though, which is a very different philosophy. So that might work often where Grind does not. Someone who's a research student in probably Cambridge, I forget who, has been developing this thing called canonical. Yeah. So
By the way, so is it, if, can I say like this? For instance, if I want to solve, write some theorem.
yeah.
So when I first, I can start by saying that this theorem state and I finalize by Grind.
Yes.
So if it doesn't work only, I have to even go for other.
That is a standard way and a perfectly good way. And if it involves a recursive function, you say fun index semicolon grind. Yes, that's right.
So at every point you can try Grind. If it is not working only.
That is correct. And I had actually written this automation. It didn't quite work well when Grind did not exist. But Lean Fro is going to do this. It's in their roadmap that when you type by, it will try Grind automatically for you without you even typing Grind. And if it Grind works, it'll tell you straight away, click on this and you'll get Grind. I mean, that's obviously a good feature, right? I had this tactic called BYY, which used to try Aesop. If you, instead of typing by, you typed a slightly different thing. At each step, it would try Aesop and would let you click and try it. And if it did not get it instantly, it would run it in the background. This was done a while ago, but it was not ergonomic enough. And Aesop is not that strong. The equivalent with Grind, I would write, except that LeanFro is going to write it. Yeah. But yes, that's a generally good policy. And this is also important because if you have a computer automation calling Lean, then you can get it to call Grind every time, right? If there's no human user in the loop, then it's a good idea to.
Available.
Huh? It goes to everything in the environment. So if you load them in the environment, yes, exactly. So if you load them in the environment, it uses everything. And there are also things like, so there are two additions to Grind, which I can say you can, let me go to smallest is here. Okay, so this one I'm going to just comment out for now. But yeah, you can see Grind's proof and how it worked here. But here I said Grind smallest. There are two versions, sorry. I did not have any case of this. Okay, so did I label some things Grind? I did, right? So Isn't there any grind annotated thing here? Okay, I'll go to quick sort or something. Okay, so let's look at grind. So I said grind sorted step here, telling it to use this one. But if there is a version of this called grind plus locals. Oh, no, because it's not a theorem here. Sorry. Doesn't always work. So, okay, what I want to say is there is a version called grind plus locals, which uses all the theorems in that given file. And there's something called grind plus suggestions, which uses an AI powered thing to search for what are the relevant lemmas, which may not be annotated grind, and uses them as well. So there's additional power you can do. And you can also configure just a suggestion provider of grind. So you can use a more powerful AI system to tell grind these are the possibly useful theorems and use those as well. So all these extensions are there. Yeah.
To try this grind, if it is not, you start writing at some point of time, you keep putting grind.
That's what I do. Well, okay. No, so there are certain cases where you wouldn't do that. Obviously, like with quicksort, I haven't done it. So there are certain cases where grind will not work, but you know what to do. For example, you can use fun induction if it's defined as a recursive function. If it's defined with pattern matching of a complicated sort and pattern matching is not going to work, then you put match in the same way in the proof. Try grind in other subcases. But also, if I want to show an example where things are more serious, like when I say, oh, this one did it too easily. So sometimes when you want to do proofs like by induction, you have a let or have which gives you the previous state call inductively. I mean, so the previous case is called inductively so that it gets introduced into the context and then use grind. So there are a bunch of situations where you know that grind won't do it because it's not really automatable. You just do the appropriate things. But yes. So as I said, LeanFro said they're going to do something where you have a enhanced tactic mode where grind will just automatically be tried at each step. So you don't even have to manually try it.
What about exact?
What about exact tactic? So exact tactic means exactly this term. So the term, you give the term as a term proof. So let me go back to a simple case so anywhere where I have a term proof like this, I could do the following. So let me copy this and call it an example. So let me do a couple of examples. This is nothing, but I could also do by, so here it's a pretty stupid way to do it, but exact, and I gave the exact proof. So exact is I'm supplying you with the proof. Okay, so it's exactly this. Almost always apply will also work because there are no arguments to fill in. But it's recommended you use exact to avoid errors. Yeah. Well, one is that you have LLM search and so on. We have in our own code. So you can have a tactic which may cause an external user. So then that is not deterministic at all. Okay. But built-in tactics of Lean, I'm not sure of this because Lean has concurrency support. And if you have a search tactic with concurrency, then it's often a race which thread succeeds. There may be two proofs and you're doing a proof concurrently searching for various different ones. And it completely depends on the state of the world, how hot or cold, whether you're working in Bangalore or Nagpur, which is much hotter. So your laptop speed, whatever else, which one succeeds. So there's no guarantee of determinism. Let me say that. And as far as I understand, even as soon as you introduce concurrency into any code, you are not deterministic. If you add concurrency and search, then you're not deterministic anymore. And quite good chance that some of these things have concurrency and code. But yeah.
On the tactics.
Why not? Because you're guaranteed correct. That's all that matters. No, it's guaranteed. No, that's an important point. It is guaranteed to run on any system. So one of the things Lean does is that it does not have a timeout. It instead has what are called max heartbeats. Okay, so this is an important point here. one runs into it. So they actually face this issue. If you have a timeout by a clock, then you have genuine non-determinism exactly of the sort that you want. So instead, every time a piece of memory is allocated, this is called a heartbeat. And there is a default maximum number of heartbeats, which is 20,000 or 200,000 or something like that. But you change the limits using a set option, which becomes in your code. Okay. So this means even the timeouts become deterministic. Not accounting for you giving up or your computer running out of RAM. I mean, that kind of thing, nothing has to be robust against. I mean, assume reasonable enough hardware. But what I'm saying is it's not a function of which hardware, as long as it's good enough. And generally speaking, you should not set Mark's heartbeat so high that it'll only work on your workstation, but will not work on somebody else's laptop. So that can be a controversial thing if you make things conditional on resources. But the resource control is also deterministic. And that's why you also have this question mark tactics, like hammer, which is a question mark tactic. You don't leave it there, you replace it by the proof.
Yeah.
So exactly this. So you also even simp question mark, this was discussed yesterday, is not because of breaking or changing versions in the environment and so on. So you do have various of these question mark versions, which will have a higher level of determinism. So you have fair number of guarantees that if it is a correct proof in one system, it is a correct proof in another system. There is no special reason to guarantee it's the same proof. So no effort is made towards that because that's not a use case. I don't see any use case for guaranteeing it's the same proof because Lean has proof irrelevance. What you want to guarantee is that if it's proved in one system, it's proved in another. That's all.
But it's a file that can always like unfolds the whole thing that this is what
Yeah. Those are called Boolean files. So the proofs are stored. The proofs are not discarded. So you'll see these Boolean files, you can load the proof into memory. So you notice that when I generated things by tactics, I printed, right? I had somewhat more complicated things like this one, okay? Or even with NatLE. Okay, so let's call this theorem. Yeah, 12LE 18. So you see this whole proof, which was generated by the tactic, my crudely written tactic, is written as a term. This information is not discarded. It remains in the Lean's environment. It remains in the Lean's Olean files. So if it's really a question of auditing, you might want to go to look at the Olean file. But there are more serious issues, and this is where you have this comparator approach. What if you use metaprogramming which quietly change the meaning of some things, which allowed things to accept, etc.? So if you go to, so Lean has a thing called comparator, which is the highest degree of security, where you're supposed to have one challenge file. The challenge file is supposed to import only MATLAB or standard libraries, none of your libraries, and have only a statement of the theorem. So anybody can inspect and see the statement is there. And the proof file will import this statement and prove this statement. So this defends against all kinds of metaprogramming attack. And if you follow the strict rules, it even defends against attacks like going and editing on your disk the Lean compiler to replace it by a bogus one. I mean, if you follow the comparator rules strictly, you can guard against all sorts of failures in Lean. So Lean is very pragmatic language. So reality is that when you talk about security, security is very different between a good faith user and an adversary, right? So when you're working in Lean in VS Code, the assumption is your goal is you really want to prove things. And you are not trying to prove false things. You're trying to write correct programs or prove correct mathematics, etc., etc. So for efficiency, various checks are turned off. So you can hack around within VS Code interpreter. While comparator is, so there are degrees, comparator is against really adversarial attacks. It's against Cloud Code generating something which is supposed to just pass your tests. And Cloud Code is very happy cheating as long as it can get, as the result gets accepted. So it's against, or of course, it need not just be Claude code. There's $1 million price problem, and a human wants to cheat and get a proof of the Riemann hypothesis and claim $1 million based on this. So there is the very secure way of doing things against people who are malicious users and good faith users. And so all these are accepted. There are practices with any number of things. As I said, but you can share the Olean, but if somebody else doesn't share the Olean and you source the lean source, which is the normal thing, there's no guarantee the other person will have an Olean with the same proof. What is guaranteed? They'll have a correct proof, you have a correct proof. That's all. And in practice, that's the only guarantee that you need. So are you sure that, so the question is, are the definitions in the math library sound? I think this for the same reason as open source and much more. See, MATLib has relatively few definitions and lots of theorems. If some definition, at least a relatively basic definition went wrong, then it's very likely that you would fail to prove at least one of the theorems you expect. Or someone will accidentally prove a false theorem. In addition to a human review process, so this is a general thing with Lean, that if you make your own definitions, how do you know that the definitions are correct? So typically you do this. This was done in liquid tensor experiment. When I formalized the Ganam with Anand, we did it too, and so on. You prove a lot of extra theorems. That's what these example things are for. You don't actually care about those theorems, but those theorems are to test that your definition is correct. But I also showed this quicksort and sorted and monotone, right? You make multiple definitions and you prove that one definition is equivalent to the other. Or you make a definition which is very general. In a special case, you may have a much easier definition. Make that separately so you can see that is correct and prove that the general one specializes to this one. So there are various ways in which you can get, like Patrick says, superhuman level of correctness. Perfect correctness will always be an illusion, but you can get a very high level of checks. So all these things I'm telling are ways of getting very high level of checks. In practice, if you're running lean code, I think the only real vulnerability is the code generation, which may have, I mean, the code generation, and you saw in the C program, lots of lean libraries imported. Those may have bugs. And that, I mean, Ilya explained some things about. Well, Lean itself has a metaprogramming in Lean. You just use Lean as a programming language, as a metaprogramming language to write tactics. They're very pleasant. Metaprogramming in Lean is actually easier than I think almost any language. It's quite pleasant. It's not trivial. There's a whole bunch of metaprogramming examples in this repository also. Yeah. But the other thing is, because Lean is written in Lean, if you see grind, that's what I was about to do, and we went off to something else. So if I see grind, for example,
When you say metaprogramming, what do you mean?
So metaprogramming means where you're working with not the behavior of programs, but their inner representation. You analyze, you generate, modify programs. In Lean, this has a twist to it. There are two levels of inner representations. One which is syntax, and macros are manipulating at syntax level. And one which is what are called expressions, which are really in the foundation of Lean. You can metaprogram at both levels. So you can generate a Lean program from a Lean program itself. Okay, so yeah. So one of the things where I did this, I'm not going to try to explain it now, but somebody talked about having a small, so one of the previous workshops as illustration, I created a language called a tiny imperative language. Yeah, I think Ilya had an example of, Deepak had in his talk, he talked about a small language. So here's a small language. This is for showing this is slightly advanced. I'm not saying it's at this. So it's a tiny imperative language with assignment, conditional, while, and print. And a shallow embedding. You've heard shallow and deep embeddings many times. And so what I did as an illustration in another workshop and explained is define embedding of this in Lean. So there's a Langur program, and I have to go to one more thing to show you. And there's a program interpreter, and let me show it in action. Langur leaps. Good thing about making puns is it opens room for making even more puns. So instead of running, which you run in every language, since this is a langur, it climbs or it leaps. So here is a program in LeanLang, and n is 3, m is 4 plus 5. If this, then else this. It branches on this decidable condition and returns a value. So here is something that adds the first 10 numbers. I'm just showing when I said metaprogramming is easy in Lean. Here is something which adds the first numbers. I showed the id.runDo. And here, when you hover on the return, it tells you what the final variable state is of all of the variables. And this is, I say hash leap is a new command I have introduced, which simply runs a program. Oh yeah, so this was my fanciest example. It's a primality testing for Lean, and I think I have even more fancy. I define primality, which so leap is a program, climb is climbing, of course, the Langur's climb, as we all know. You feed in n and you write a program and it evaluates it. Okay, and so far it doesn't take inputs because I just spent a little time. It's a baby language for illustration. So what I mean by meta programming here is I've introduced my own commands, I've introduced my own syntax. Someone asked adding tactics, as you would guess, this is a level of complexity actually beyond adding tactics, adding a DSL. So here's the shallow, this is called a shallow embedding because 57, if I hover on it here, is actually a Lean natural number. So it's using Lean's own natural numbers for assignments. It's not re-implementing natural numbers. This means any theorem about natural numbers is, or any function that's there in Lean is already available to you. And similarly, I'm using Lean's own Boolean. So and is a Boolean function in Lean. I didn't have to define it. Or equal to 1 is also, I didn't re-implement equality. So if it was a deep embedding, that means I have to re-implement natural numbers. And using Lean's constructions. And similarly, when I use any operation, addition, multiplication, equality, I would have to support it using an inductive type in Lean and so on. So the types would first class types. I would not use Lean's own definition of natural numbers. I would have my own definition. In this case, for natural numbers, that's a very silly duplication because NAT is written in NAT, in Lean itself. I mean, so I can click on NAT definition. But if the language was a little bit more different, this would make a difference. It means all the types that I use, all the operations on them, I'm re-implementing rather than using Lean's addition, which is very complicated. So that burden is there. And so that would be what's called a deep embedding. You have the language deep inside another language. You would do that if you really want to reason about the language. I want to prove theorems about this language. But I, in practical terms, will always use a shallow embedding because why throw away all the power of Lean? I mean, why do I want to force myself to define less than or equal to? Just in this, I've used plus, I've used multiplication, I've used the parenthesis notation, I've used less than or equal to, I've used combinations of Booleans, whole lot of things. Why would I implement another language if I ever wanted to run? And generally you would trust Lean, so you don't need have that reason. You could do something which is have a deep and a shallow embedding and have a theorem saying they're equal to each other. Though that would be if you're kind of a little paranoid, but yeah, so that's right. Yeah. I've also used Lean's nice facilities like the info view. So when I print, it doesn't print somewhere else. It just shows it in the info view with this blue thing. Yeah, so this is just, I mean, as I said, over the next few days, if I don't think I mean, if people are interested, you can catch and ask, and we can look at the implementation of this. This is kind of a little bit of an Apex thing in this course, which, yeah, is, which even Agda has. I think you should ask Ilya. I don't know. So that's the short answer. But Ilya is around today. Ask him. Yeah, he might know these things. So holes and refine. No, you can put a placeholder. Okay. So maybe I think I don't know if this is similar to Idris, but I will show you what it does have. Which might or might not be an answer to yours. Okay. So for example, if I have this theorem, theorem 1 is less than or equal to 3. So I got into tactic mode, but suppose I don't get into tactic mode and say 1 is less than or equal to 3. So I can put an underscore, and it says it doesn't know how to synthesize placeholder. Okay, so then I can say nat.le step and put an underscore. And again, it doesn't know how to synthesize this placeholder. So this is an underscore which you can have. And then you can put further nat.le dot step underscore. And it still doesn't know how to do this. But here I can do nat.le reflect. Okay, but in this case, nat.le reflect has an implicit parameter. I put at, so it becomes explicit parameter. And I put an underscore. And this time it actually knows how to synthesize this placeholder. So in Lean, you can work with term proofs where you have partial information, put underscore. It assigns meta variables, as they are called, to this, tries to solve them. And you can programmatically also do this, meta programmatically, assign meta variables and then assign values to the meta variables, meaning create meta variables, assign values, and if they're assigned all the way, it becomes legal. This is a way when you're writing tactics or other kinds of automation, you do this. So this is there in Lean. The tactic mode rather than this underscore is more idiomatic if you're working interactively. But the equivalent of this with meta variables instead of internally is heavily used in meta programming in Lean. So yeah, so I don't know if this is the Idris thing, but I think it's maybe somewhat similar. I mean, the dash sounded a bit like that. Yeah. No, I said at nat. So if you hover on nat.le, the braces is an implicit parameter. So it just filled it in. When I say at means all parameters now become explicit. So then I illustrated that if I put a dash, it can fill it in. You can go from implicit to explicit parameters both ways. If it's an explicit parameter, you put a dash, it tries to fill it in. And if you put at, everything becomes explicit. So both of these are. There are internally make app m and so on, which you will use, which are similar to these things. Yeah, it's exactly equivalent. And the apply mode gives you exactly this. So I wrote fully term proofs. I wrote things using fully explicit, and now I'm showing underscore and successively filling in. And this underscore and successively filling in, as I said, this is what's called a meta variable. And one of you was experimenting and got a question mark something, and those are meta variables. So those are creating them, writing an expression in terms of those, and then assigning them is routinely done. But usually by people writing tactics or otherwise meta programming, users usually use tactics because that is the easier way to work in interactive sense. Underscore is conceptually perfectly fine. They have different domains. LeanArith is linear arithmetic. It works for natural numbers, integers, rational numbers, etc. Provided all your goals are linear, equalities or inequalities. Omega can handle things which are not necessarily linear, but works only for natural numbers and integers. Ring works for any ring and does ring level simplifications, but does not deal with inequalities, for example. So they have different domains of applicability. Now, what has happened is grind includes all three of them. So you don't have to, in some sense, use any of them. You just use grind. There's also what's called LIA, linear integer arithmetic, which is a little bit different from LeanArith, which is additional features which are true for integers, but not necessarily for other things with the same order structure. Yeah. So there are many of these solvers. Now grind includes basically all of them. So yeah. Anyway, lunch is ready, and afternoon we'll have Casey's talk and then Ilya's second one. Tomorrow we meet again for around say 9:30. I will set this up and people work by themselves or ask questions or any combination thereof through the morning, and afternoon will be structured. You had a question?
How does this synthesis work?
This is type class synthesis. So how does type is your question?
Yeah.
How does the command work, or what is type class synthesis? Okay, so type class synthesis means it takes a goal, construct something of this type. Okay. And it looks for instances either of that type or instances whose final codomain is of that type. Okay. If it finds an instance with final codomain is of that type, it kind of like an apply tactic. It applies it and says, okay, if I have this and this, I can build that. Then it looks for instances of these. So it does unification and it also looks for it's a backward reasoning formula. It either looks for instances directly of that form or instances where if I found other instances, it would give you that. And then keep searching, but it's not a search as such. It's a deterministic way looking for instances backward reasoning till it can fully solve. That's what it's like.
It's a decidable problem. So type class.
No, it can just fail.
No. I don't think the question
And
is
it's the deterministic. But it either
like correct. If it fails, then we know that there's no sense, or is it like
almost, but not quite. It can fail for five. So it's not no. No. So in fact, I gave a wrong answer. Let me correct myself. It is not a guaranteed decision procedure. It's only one way guide. So there might be an instance, and it may fail to find. It's an algorithm which has a little bit optimized for efficiency because type class inference happens all the time. So it has sacrificed completeness for efficiency.
okay?
So it is not complete. There may be an instance that you can construct by hand, but the type class synthesis fails to send it. It is one algorithm which tries to write the line. And if that particular search procedure fails, sometimes even because of priorities being wrong, because of it making right choices, if that particular procedure fails, it doesn't backtrack, it doesn't search, it just fails. On type class synthesis is because it's used so heavily in Lean, kind of important.
Where is it used for it?
So every time you see an addition operation between two things, it is synthesizing an instance of HR. So everywhere where you have polymorphism, operations, mapping, more than any place where you have the same thing applies to any structure, the mathematical structure like the group, it has to find out which each structure. Anything, the basic way of implementing any kind of polymorphism where some same code works in different contexts is type class inference. This means that type class inference is huge, enormously. So it better be fast. If it fails, then burden is on the user to guide it.
Okay.
You can explicitly give an instance if it works, but such a design choice.
Type inference.
Type inference and type class inference are different. Type inference means we can logically deduce this is the only type it can be. Type class inference means I found a term of this type class. So the problems they're solving are different. Type inference is the problem of deducing the types.
Yeah.
But deduction here means logically on the type must do.
Yes. So
Not literally because there are sometimes choice between mandatory and some kind of default thought out. But up to defaults and priorities, the fundamental problem of accuracy puzzles is deduction of the correct type. Type class inference is more like a search. Saying find an element of this type. But it's not an elaborate type search procedure. It's a relatively more restrict procedure. So synthesizes the term. So synthesize the term and it goes to its lab and tries to synthesize. And here I synthesize for you. Oh, sorry, I failed to say technically answer. But there is no claim that if you do synthesis in two different places, you get the same element. If you're going to get if when you synthesize, there is no claim of uniqueness of the synthesized type. If it fails, it fails. And I mean, if your type class instance is not unique, then it's your responsibility that wherever you lose it, the answer doesn't depend. I mean, there are two instances.
okay.
And those instances will give you a different value for your fund. That's your fault. So you have to ensure that if there's more than one instance, it doesn't matter. That is where you use them, how you use them, doesn't depend on which instance.
Type class inference the same as type inference.
Not at all. Because type class inference is I manage to synthesize.
Why do you need to synthesize it? Like, don't you have a just infer what the types is or type classes?
You don't infer what the type class is. You're not inferring the class. You're inferring a term of the class. Okay, so like if you are not so type class, you're not inferring the class. You're given a type of a special sort. So type classes are special sort of type class. It's more like finding a proof. Let me put it this way. You can think of type class automation, type class inference. In fact, it is a way of finding a proof. You're given a theorem. Type class is like a theorem.
Right.
Type class inference is a kind of proof automation to find the proof of that theorem. Except that instead of a proof where what the proof is irrelevant, this is data you're finding. So you're finding, I mean, in the sense of proof is nothing further, it's just true or false. Here you're going to make use of that. But it's more like proof automation rather than typing. Finding a member of a type class is like finding.
You're finding a proof object for
Exactly.
proof obligation.
Exactly. It's like that, except for terms instead of proofs.